Let's solve a linear regression problem using PyTorch. I'll import NumPy as NP, Torch, TorchNN as NN, and Matplotlib PyPlot as PLT. NN stands for Neural Network. It has useful modules for neural network computations. First, I'll prepare clean data for reference. I set the slope to 0.5 and the intercept to 1. I generate x values from -10 to 20 and then calculate corresponding y values. We can plot x and y values using Matplotlib's scatter function. I'll also draw vertical and horizontal lines using axvline and axhline functions. I'll create noisy data by adding random noise to the clean data. I set a random seed for reproducibility. Then, I generate noise data using the standard normal distribution. I multiply the noise values by 2 to make the noise bigger. And, I add the noises to the clean data. Once again, we can plot x and y values using Matplotlib's scatter function. Now, I will prepare 2D tensors containing the noisy data, which we use for training. First, I create a PyTorch tensor from the x values and call it xtrain. I'm calling the unsqueeze function to add the second dimension so that it becomes a 2D tensor. It's a matrix where each row corresponds to a data point. The shape of xtrain confirms it's a 2D tensor with 30 rows and 1 column. Xtrain is the input data for training. Then, I create another PyTorch tensor from the y values and call it ytrain. Again, I'm calling the unsqueeze function to add the column dimension to make it a matrix. Ytrain is the label data, providing expected values during training. We can confirm that the shape of ytrain is the same as that of xtrain. Now, our training data is ready for a linear regression model. TorchNN has many modules useful for deep learning. TorchNN has a handful of linear layers. In this session, we'll use NN linear layer. It applies a linear transformation to the incoming data. We will use NN linear to apply a slope and an intercept to input values x to estimate output values y. Let's start coding a linear transformation with PyTorch. As a reminder, we import TorchNN as NN. I'm calling torch manual seed to fix the seed value for reproducibility. I create a new linear model using NN linear passing 1 and 1. The first one is the size of each input. Since each input x has only one value, we specify 1 there. The second one is the size of each output. Again, each output y is one value, so we specify 1 there, too. Inside NN linear, it randomly initializes a slope and an intercept. This is why we fixed the random seed. We can access the randomly initialized slope and intercept values via the parameters method, which returns a generator object. I convert the generator to a Python list and check the first and second parameters, calling the item function to get a Python native scalar value. As you can see, the slope and intercept values are randomly initialized. In deep learning, we usually use terms like weights and biases. Weights multiply input values, and biases add values. Well, in our case, we only have one weight and one bias corresponding to a slope and an intercept, respectively. In fact, we can access the weight and bias properties of the model, which is simpler to obtain parameter values. We can call the item function to retrieve the Python native values, as we have only one weight and one bias. The linear model takes xtrain values as input to calculate predicted y values using the randomly initialized parameters, namely, slope and intercept. As I feed xtrain to the model to get output, we call this process feedforward. Y hat is the predicted y values given input xtrain. Printing y hat shows 30 predicted y values. They are different from the true y values as the slope and intercept were randomly initialized. One more thing to notice is that it prints grad fn at the bottom. The grad fn of y hat remembers the function that created it. As the model multiplies matrix xtrain with a slope and adds an intercept, it's called add for addition and matrix multiplication. We'll talk more about the grad fn property later when we discuss the automatic differentiation mechanism. After the feedforward computation, we calculate the loss value. This code implements MSE. PyTorch provides MSE loss class that we can use to calculate MSE. As we can see, the result is the same. So, we'll use MSE loss as our loss function. Once we have the gradient of MSE, we can decide whether to increase or decrease parameters. If the partial derivative of MSE with respect to a hat is positive, we should decrease a hat, which makes the slope less steep. If the partial derivative of MSE with respect to b hat is positive, we should decrease b hat, which makes the intercept lower. So, we are applying changes to the parameters in the opposite direction of the gradient. If the partial derivative of MSE with respect to a hat is negative, we should increase a hat, which makes the slope steeper. If the partial derivative of MSE with respect to b hat is negative, we should increase b hat, which makes the intercept higher. Well, in this example, we are increasing parameters too rapidly and overshooting the true regression line. We need a way to control the rate of change when updating our parameters. We use a learning rate to specify how fast or slow to apply changes to our parameters. In this example, I set the learning rate to 0.1 so that we update the parameters using 0.1 times the gradient. Now, the parameter changes are modest. We call the learning rate a hyperparameter and distinguish it from the model parameters such as slope and intercept. The model learns the model parameter values from training data, whereas we configure hyperparameters as they are external to the model. So, when we train a model, we adjust the learning rate to ensure the loss value decreases over training iterations. If the learning rate is too big, the updated parameters may overshoot the true values. On the other hand, if the learning rate is too small, the parameter changes too slowly, and it would take too much time to reduce the loss value. To simplify the optimization process, PyTorch provides a variety of optimizers in the TorchOptim namespace. Advanced optimizers like Atom can even adjust learning rates dynamically for each parameter. We'll use the simplest optimizer, SGD, which stands for Stochastic Gradient Descent. It uses a fixed learning rate that we specify to update parameters, as we've discussed previously. To create an SGD optimizer, I'll pass the model parameters and a learning rate. First, we call optimizer 0grad to clear the gradient values. Then, we feed input values to the model and calculate the loss and the gradient. Finally, we call optimizer step, which will update parameters using the gradient and the learning rate. There is one last thing I haven't mentioned, which is backpropagation. It calculates all the partial derivatives from the loss tensor backward to respective parameters like the slope and the intercept. Let's discuss that now. To understand the backpropagation, we need to know a computational graph. In the feed-forward computation, we multiply x-train by the weight and then add the bias. After that, the MSE loss function calculates the loss using y-hat and y-train. As a result, the chain of computations forms a computational graph. Given the loss value, we want to calculate the partial derivatives with respect to the weight and bias. Therefore, we also need a backward connection in the computational graph. This is where the grad_fn property comes into play. The loss tensor shows the grad_fn property pointing back to the MSE loss, which computed the loss. MSE loss involves y-hat, which shows the grad_fn property pointing back to the linear operation. The linear operation involves matrix multiplication and addition, which uses two parameters. The slope and intercept parameters show that the requires grad is true, which tells PyTorch that we want the partial derivatives with respect to these two parameters. So, the feed-forward computes the loss value. Each operation in the computational graph is differentiable, meaning we can calculate partial derivatives for them. Hence, we can follow the chain of operations backward to derive the partial derivative with respect to each parameter. More intuitively, we can calculate how the change in each parameter affects the loss value. We call this process backpropagation. In summary, PyTorch has a built-in engine called AutoGrad that can automatically compute gradients for any computational graph. To perform backpropagation, all we need to do is call the backward function on the loss tensor. It calculates the partial derivative of each parameter and stores it in the grad property, which the optimizer uses to update the parameters. We are ready to solve the linear regression problem using PyTorch. We'll perform the feed-forward computation and backpropagation to update parameters in a loop. We call one iteration an epoch. So, we repeat the training loop for many epochs until the loss value converges into a small value. Here, I'm using 300 epochs and printing the loss value at every 30th epoch. As you can see, the loss value converges after 180 epochs. Let's check the final prediction of the slope and intercept. The slope is 0.52, and the intercept is 1.01. These values are very close to the true values of 0.5 and 1.0, respectively. Not bad at all. By plotting the linear regression line, we can visually confirm that the model has learned the parameters from the training data very well. It's working. There you have it. Now, you should be able to train a linear regression model with your own training data. I hope you'll enjoy doing so.